Welcome back to Chapter 1.2, Expectations, Variance, and Covariance as Geometry, Part 10 of 10, our finale. In Part 9, we built the covariance matrix sigma and found it symmetric and positive semi-definite, with the quadratic form W transpose sigma W giving any portfolio's variance. We almost never know sigma exactly though. In practice, we estimate it from data and rescale it into the correlation matrix, the heat map of cosines you will actually plot in the notebook. Then we wrap up the whole chapter and look ahead to the work it sets up. A last practical note for the notebook. We almost never know sigma exactly. We estimate it from data with the sample covariance matrix, and we usually look at the correlation matrix. Sigma with each entry divided by the product of the relevant standard deviations, so the diagonal is all ones and every off-diagonal entry is a correlation between -1 and 1. That rescaled matrix is what a correlation heat map draws, a grid of cosines, hot where assets move together and cool where they move apart. The most honest one-glance picture of where diversification can and cannot help. Getting comfortable now with sigma's symmetry, its positive semi-definiteness, and the quadratic form W transpose sigma W means Chapter 2.1 will feel like a sequel rather than a fresh shock. Now it is your turn. Open the notebook for Chapter 1.2, Covariance Matrices and Correlation Heat Maps. You will download returns for a handful of assets. Build the sample covariance and correlation matrices, draw a correlation heat map, and confirm numerically that combining low correlation assets lowers portfolio volatility. Maya's experiment, but with real data and many assets at once. 3 check questions to chew on before you start. First, recompute Maya's expected return and variance for a 70-30 split under the opposite movement scenario, and ask whether the portfolio is still less volatile than asset 2 alone. Second, if 2 series have standard deviations 0.15 and 0.05, explain why a reported covariance of 0.012 must be wrong, and take the largest covariance they could have. Third, give 2 variables that are uncorrelated but clearly not independent, and name what covariance fails to see. To close Chapter 1.2, expectation is linear and never needs independence, so expected portfolio return is a simple weighted average. Variance and covariance are nonlinear, so the variance of a sum carries a cross term, twice the covariance, and that single term is where diversification comes from, as Maya's 3 scenarios showed by pushing volatility below her safest asset. Centering variables turns the algebra into geometry. Covariance is an inner product. Standard deviation is length. Correlation is the cosine of the angle. Uncorrelated means perpendicular, and the bound that correlation never exceeds 1 is Cauchy-Schwarz. Stacking all the pairwise covariances gives the symmetric, positive, semi-definite matrix sigma, whose quadratic form is any portfolio's variance, and which is the same kind of object that Week 2's matrix regression inverts. This is the algebra the rest of the camp stands on, and Chapter 1.3 will put it to work estimating these quantities from real data.